Good afternoon, everyone, and welcome to the U.S. Pavilion here at the World Conservation Congress. This is a U.S. Department of State public diplomacy initiative, and we are so happy to have you here with us. It is my honor and pleasure to introduce the next speaker who will be giving a Hyperwall presentation. It is Dr. Kathryn Sullivan of NOAA. So if you've been enjoying NOAA's Science on a Sphere, this is the lady who runs all of NOAA. So we're so happy to have her here with us. And she'll be speaking about the Marine Biodiversity Observing Network. Dr. Sullivan.
Well, thank you, Nicole. I'm delighted to be back here today, and I've got several key colleagues in the audience who really are the hands and the brains behind the work that I'm going to feature here. I'll introduce them to you as we get underway, because if you have any really pointed questions, I'm going to defer to them for the real answers. So what you're seeing here, as the title behind me says, is a really fabulous loop from some of the Pacific Remote Islands Marine National Monument and the Marianas Trench Marine National Monument that have been captured just over the last 2 field seasons by NOAA's ship, the Okeanos Explorer. The Global Foundation for Ocean Exploration has been our video partner in this. And we wanted to feature it just to remind you all of how richly diverse and absolutely spectacular our underwater world is. And a theme or a motivation for both our work and my talk will be to emphasize also how very little we know about that environment and how important it is that we continue to advance our knowledge and that we develop tools that help us better understand and work with our growing body of knowledge and information. So let's zoom back just a little bit, like maybe to here. We all come to this conference, the 9,000 and some odd people gathered here this week. We come to this conference from all over the world, and I mean all over this world, from literally every corner of this planet. I had the extraordinary privilege in my former life of having this view. This was my view out my office window. It was the sort of sight that lulled me to sleep each night. If you woke up for a bit in the middle of the night, you would take 5 or 10 or 15 or 20 minutes and see again what part of the world that you're over. And I just sort of have to do this because astronauts have to do this, and because a hyperwall almost starts to give you a sense of how spectacular the view is. Astronauts always comment on how glorious and sort of inspiring and idealistic the view is. No boundaries, an entire integrated planet. You get a sense of the systems, as you can tell from this loop. But in point of fact, the world that we live on is much more complicated than these glorious images suggest. And that's because these kind of critters live on the Earth. Human beings, that's me on the left and Dave Liesma on the right. The world we actually live in, the challenges that we face are more complex than that glorious, simple, space-based view provides. And that's true on both an experiential level for an astronaut, and as I'll show as we go through the talk, it's true in a scientific sense as well. And I certainly found in my 3 space flights, I could never get enough of that view. But as a scientist and someone who always had been curious about and passionate to understand our planet, and understand it in a meaningful way that could actually help us live more wisely and well on this planet, it wasn't enough to just look out the window and have the pretty picture. Satellites, any satellite from a space shuttle to NASA's Earth observing satellites and NOAA's Earth observing satellites, they can give us fabulous pictures, but our challenge is really to deepen that picture and build the complete understanding that we can use to inform our actions. So that's what we'll talk about here today. And as we all know, our planet is changing, and in many ways and in many regions, changing quite rapidly. The scientific evidence is abundantly clear. I've featured just 4 good indicators. This is just data. This is what you measure. Arguing about this would be like arguing with your doctor when he took your pulse. No, it's not really 104. Yes, actually it is. I just measured it. Carbon dioxide rising in the atmosphere, sea level rising, global temperatures, average global temperatures rising, and ocean heat, the amount of heat the ocean itself is storing. And heat, of course, is the engine of ocean circulation. That is changing too. So the scientific signals and the scientific evidence are abundantly clear, and as we all know, the evidence is also increasingly very visible, very tangible, very real in our human experience as well. Whether it's intense drought featured in the upper left, calving and retreating glaciers, changing frequencies of intense storms, large scales of coral bleaching. I could go on and on and on, but the symptoms are as real, and the evidence in our experience is accruing just as the scientific evidence has been accruing. So how do we get a handle on these changes? What tools, what abilities do we have to try to bring better information into our world and make more informed decisions? Satellites are fantastic tools that give us a kind of capability to tackle these challenges that humankind literally has never had before our generation. We are the first generation of human beings to have the ability to effectively take a snapshot of conditions on the globe in a quantitative and a rigorous way that we can transform into action. I'm showing you here just a small selection of some of the kinds of information that satellites play a critical role in providing us. And I will emphasize as I go through the talk, what you're seeing here may look like the picture a satellite took, but none of these representations are just the satellite picture. In each of these cases, it takes the satellite measurement added to in situ data and other careful analysis to make this first information product. But look how amazing it is to be able to see the amount of precipitatable water in the atmosphere, to see the winds globally almost simultaneously, to see ocean circulation at the scale where you can see the eddies that really are the mixing in the ocean, to see the biosphere itself, the living planet, at least on the surface of the Earth. Really remarkable capabilities that, again, are unparalleled compared to any other time in human history. And the urgency, the need to really bring this information together and inform human decisions has also been becoming clearer and clearer in the policy and political arena as well. Testament to that, probably the most vivid testament to that, is the fact that the countries of the United Nations have come together over the last several years and identified these Sustainable Development Goals. There are, as you see, 17 of them. That's actually a pretty big number. And under each of these, there are a number of actions and targets that have been identified, and those number in the hundreds. And here's a quandary with the Sustainable Development Goals. What do you do with that list? Do you pick one? Do you pick a topic you most care about? Do you choose a color? How do we really tackle these? Because this just looks like a deck of cards. Pick a card, any card. But that's not, in fact, the nature of these problems. It's not, in fact, a way that will get us to the kinds of solutions that the Sustainable Development Goals are meant to help us generate. So here's a different way, a more useful and practical way to look at the Sustainable Development Goals. This is a schema that's been developed by the Stockholm Sustainability Institute. And it is basically a logic model. It says to us, look, there are 3 different categories of goals, and there are important relationships we must understand between those categories. On the bottom layer of this wedding cake, you have the 4 Sustainable Development Goals that tackle life in the water, life on land, clean water and sanitation, and climate factors. Earth observations data of the sort that we will be talking about today are indispensable to getting a handle on those drivers, and they drive everything else in the upper layers of the wedding cake. The next tier of the wedding cake is society, and I think, as everyone in this hall certainly knows, it is beyond folly to imagine you can have a healthy and viable and durable society without a vibrant and durable environment underpinning it. So to gain any of the societal goals you want, good health and well-being, zero hunger, any of those, you must be accounting for the natural environment, the planet on which we live. And without a healthy and functioning society with some fair degrees of equity and equality and vitality to them, without that, there's no way to really achieve the economic Sustainable Development Goals shown in the upper layer. All of this then reminds us that even an economic policymaker, even someone working to eradicate global hunger, even someone caring about quality education in that middle layer, really needs to have their work informed in appropriate ways by knowledge of the Earth, by Earth observations, data, and information. How do you do that, though? Because historically, the players, the people who live in that bottom layer of the wedding cake, are geeky scientists who go collect vast quantities of obscure data, analyze it in complex ways, write it up in a very obscure foreign language, and print it in journals that no one but their cousins ever see. How do you get information, and more importantly, how do you get the insights from that information to the decision makers in these other tiers? And the answer is through a series of steps that many groups have been working on for quite some time. I lead the US contingent to a group called the Group on Earth Observations. And that group has been working to help complete this, make the links of this chain for quite some time. So we're going to take the rich observing systems of the sort that I've been illustrating you. We're going to add them to in situ data and information such as you see here. All of this is predicated on a global regime, a global set of agreements for free and open sharing of the data. So any of the data NOAA collects are free and openly available to anyone else who can use them. And countries around the world have embarked down this path for many decades. Nobody, no country, no weather bureau can make you a weather forecast without data from the entire globe. So it is really critical that all countries measure what they can and share with everybody else this underlying foundational data so that everywhere in the world, from a college campus to a small entrepreneur to a civic leader, the data are available for their use and for their need. This graphic shows you just some of the additional kinds of sensors that organizations like NOAA put into the environment to add the quality, to add the calibration, to bring the realism and the specificity to satellite data. From sonar data to map the bottom of the ocean to surface meteorology, it takes, as I said before, not just the satellite picture, but really the fusion of these many strands of data to begin to turn data into actionable information. And that's kind of NOAA's bread and butter. So, this group on Earth observations came into being 10 years ago to do these two things, to drive the sustainment of observing networks, satellites, and those in situ gear I showed you just a moment ago, and to advocate for increased and widespread open sharing of data. And then thirdly, to do the thing we talked about with the Sustainable Development Goals, to look at the decision needs of an economist or a social scientist or someone responsible for public health, and to connect the dots, to create the capabilities and a smooth path to move the science data through the analysis and information and into actionable form that could meet that decision maker where they are. And that's this sort of a chain. We get some snapshot of the Earth from our satellites and our sensors. We have to verify and make sure the measurement is sound and accurate. We have to analyze it and then not just put it in a journal, but actually package it in a way that is oriented towards the decision maker that is looking for some guidance. That's the sequence, the simplified version of the sequence of steps, the value chain, if you will, that connects these spectacular scientific capabilities to societal benefit and societal gain. So, let's talk a little bit more about what we're doing in GEO, because we're launching a very new thrust in GEO. We've worked that link of chain in the forest arena in an initiative called the Global Forest Observing Network. We've worked it for food security in an initiative called the GEO Global Land Agriculture Monitor, which now helps inform the famine early warning system that the United Nations operates. And we're now turning our attention within GEO to marine biodiversity in really very exciting and powerful ways. The label for this is MBON, Marine Biodiversity Observing Network, because again, no information without the observations. We must take the pulse of the planet, this very rich, dynamic planet of ours. You have to keep taking the pulse repeatedly to really gain the understanding that we need to have practical applications and really yield societal benefit. Again, more of the magical critters that we've seen on these cruises, dozens of species seen for the first time on these several cruises. And the MBON initiative is working on several pilot projects to really drive this home and connect all the dots on that chain. I'm going to talk to you a bit about the ones we're doing in Florida and in the Monterey Bay in the United States. And I want to say right up front, I'm here as the administrator of NOAA, but MBON is both a very multifaceted United States contribution as well as one that involves many other partners within GEO. So within the United States, it's NOAA, it's NASA, it's our Integrated Observing System Network, and our Department of Interior's Bureau of Ocean Energy Management, all working together. No one cares too much about labels. We just want to get the tools out there that can actually help us understand and better manage our spectacular ocean realm. So what are we doing? Let's start with the snapshot part, as we talked about. So this again is actually a model. This is a computer model that models ocean circulation, the full depth of the ocean. But we're showing you here just the surface layer, and the colors indicate sea surface temperature. So you're seeing where cold and warm water flow, where they mix. These spectacular eddies off the tip of South America, for example, and up in the Gulf of Mexico and off the east coast of the United States. One kind of snapshot, if you will, satellite plus other data plus analysis plus modeling, but we can see the ocean at this scale. We can see the deviation, how unusually hot or cool is the ocean right now. The colors on this is from NOAA's Coral Reef Watch. The colors here, warm colors show you up to 5 degrees hotter than the average over a number of decades, and blue ones show you cooler. And you're seeing a period of time here through 2015 and 16. We've been having the most persistent and expansive coral bleaching event that we've seen globally ever over the last 3 years. So temperature, deviations, anomalies, the unusual conditions. This is actually chlorophyll concentration. Again, partly from satellite plus in situ. Chlorophyll is used as a proxy for phytoplankton. It's the green stuff. It's the living base layer of the ocean. And where you see more green, you've got a higher abundance of chlorophyll, richer phytoplankton, more productivity in those waters. And you can see the subpolar gyres are concentration points, the west coasts of countries, where upwelling and current flows bring cold, rich, nutrient-rich water up to the surface. That's where you get these glorious plant blooms. These are basically blooming flowers in the ocean. So we can get all of those sorts of snapshots. We go to the next stage. We've got to verify the data, and again, a plethora of tools and techniques that are used to do that. In the middle of the bottom, you see a trawl net coming back over the stern of a ship. The only way we can really know the abundance of different kinds of fish in the ocean is to go out and do some in situ sampling and apply the data to population models. Out on reefs and in very diverse habitats, complex habitats, direct observations, such as with divers, are needed to take the information to the scale, to the specificity that we really want to get to in order to understand the biodiversity of the ocean. The presence, the abundance, the phenology, the genomics, what is really there and how well can we really know that. So a lot of in situ work, all the way down to the DNA level in many cases, to provide the texture and the meaning that we need to make this information useful. Then analyzing it. So you've got a bunch of measurements, putting it into an analytical framework, putting it into a conceptual framework, and beginning to fuse pieces together to make a more complete total picture. Today's data merged with the historical data, merged across appropriate geographic scales, so we can start to be sure we understand the time and space variation of the biodiversity of the satellite data of the ocean itself. And then moving on from there to what I indicated before, packaging it. How do we go from the geeky scientist, what elements of information does a decision maker really need? NOAA produces 20 terabytes of data a day. I promise you there's no one out there that needs 20 terabytes of data a day. They need and they crave that little dollop of information that's information, not data, and that connects into the questions they're working on and adds insight, adds illumination. So the packaging problem is about that. It's about understanding the question set, understanding the decision framework of someone who's not a scientist, might be a political leader, might be a minister, minister of the environment, a minister of agriculture. What is their challenge? What are they trying to solve? And what elements might earth science and observation add to their repertoire? That's the mutual understanding chain that needs to get connected. And I'm going to focus just on two quick examples here. On the left, I'll show you a few scenes of the MBON portal. We're creating a couple of portals where you can find all of this information in very findable, accessible, zoom in and zoom out fashion. And then on the right, I'll show you more of this, but a very exciting, very new capability that we're delighted to really be telling all of you about for the first time, the ability to map globally ecological marine units throughout the world's ocean. So let's take a little closer look. This is what the US portal for the Florida Keys looks like, and you'll see how this just runs through as if you were a user clicking in and interrogating this portal for certain information. You can see it's showing you different polygons that are showing you fish census. So where do you have what density of fish? Many strands of data accessible through this portal with a user interface that recognizes, I don't know what your question is, so I want to give you a very easy keyboard. And as you work through your question, you say, I wonder what this is and that is, and can you also show me the temperature? And be able to put that in front of you in a comprehensible kind of way. Throw the sea surface temperature in, put it in another viewer, so much more accessible, usable, sort of just like our cell phones, make all the complexity not your problem, but make the information and the ability to mix it in the ways you need pretty ready to do. So we get all of that analyzed. Here's the new ecological marine unit map. We're zooming into right where we are, and you'll see in a moment, cylinders will pop up on the map. These cylinders are the data layers from NOAA's World Ocean Data Atlas, 52 million data points about the ocean, about the physical and chemical characteristics of the ocean at 105 depth levels. So salinity, temperature, depth, dissolved oxygen, phosphate, the key variables that enable life throughout the ocean. We represent it as disks so that you can see sideways and see the layers. It's actually a continuous grid. The red donut there on that stack is a layer of the water that's hypoxic, that is depleted in oxygen. That's going to be hugely significant biologically. So to be able to see that over a whole global expanse, to be able to see where it thins out or where it mixes with some other water mass, we're just sort of showing you representationally the population we've got in here now. This is a global framework. It right now contains the average over the entire World Ocean Data Atlas, a 50-some-odd-year record. The team will now go back and start time slicing it and providing the ability to look at it in different dimensions. Right now, we've just got the very first initial framework established. And I want to give a shout out here to Woody Turner from NASA, to Roger Sayre from the U.S. Geological Survey, to Drew Stevens from ESRI, the ESRI Corporation. They're really the nucleus of the team, the multi-agency team that's been pulling this together. It exists, it is live, there's a lot of work still to do to give it the dexterity, if you will, to look at different time slices and more carefully at different depth slices. There's a whole nother database called the Ocean Biology Information database that's not yet been loaded into this, but imagine being able to add into this what's known about fish stocks, what's known about coral species, and imagine and really think how fabulous it will be to be able to continually populate and improve this with data from any cruise, from any expedition as we go forward over time. So it's now really just, I always think of it as a Christmas tree that we all can hang ornaments on now, and over time really come to a richer understanding of our ocean, and also help ourselves understand what's the next science data or target we should go after to make this even more useful. But it's a hugely exciting thing, just completed and brought to this stage a few weeks ago, and you're among the first people to get a quick look at it. That's Roger Sayre from U.S. Geological Survey there, by the way. Woody, where are you? There's Woody and Drew lurking over here. So like I said, if you ask me anything really hard, I'm talking to them. So we've been through all of those steps and working on developing the tools and capabilities to package and deliver information in a way that really is information, not just raw data, and that really can fit into the kind of framework a decision maker facing real world problems might be working in. And I show here just to remind us all of some of the societal questions, societal needs that these tools and these flows of data can help us tackle. That picture on the lower left is a hand going into the water in the United States Great Lakes not many months ago. Lake Erie, of the 5 Great Lakes in particular, seasonally has massive blooms of algae, often toxic algae. And you can see how dense and thick that became in the most recent bloom. Getting to where we can monitor and even predict this has been a tremendous step forward that NOAA and our partners have made of real societal importance, because some cities and towns draw their drinking water from the Great Lakes. And if the concentration of these poisonous bugs and critters gets high without them knowing it, they could pull that in and contaminate their entire water system, sicken people in their community. And if you contaminate the water system, you're going to have to shut it down for an even longer period of time. So NOAA operates a Great Lakes forecast system that sends forecast alerts to those water managers so they can shut the valves on the system before it gets contaminated. It's better to find a way to supply water by a different path for a few days or a week while the bloom is happening than to lose the municipal water system for months. So we're talking communities of hundreds of thousands of people. So this is the sort of, just a good small example of sort of what I call actionable intelligence. It really is useful to you to take an action that either provides the outcome you were after or averts an outcome that you really want to avoid for societal benefit or to avoid because of consequence to the resource itself. These tools don't just enable us to manage our interface with nature for human benefit better. They actually also very much will help us steward and manage our natural resources more wisely as well. So this is, if you will, sort of the intellectual and human ecosystem that it takes to make this sort of thing happen, just expanded and shown as part of a world. It is, in a sense, a parallel world to the physical world that we live in. We've touched on many of these. We've got cities and NGOs and utilities and businesses, and we need to do all of these things. We need to monitor and analyze. Modeling is another form of analysis. That plus the data we now have as we take the pulse of the planet actually enable us to predict the weather, to predict that Lester will go away and leave us alone, to predict that you're going to have a great gob of green water off your lake in a couple of days, close the water valves, to predict when a staple food crop is likely to fail and impoverished countries will be in a real food security crisis. This capacity to predict what's coming has never existed in human existence before. It is very novel, very new, and we are still babies in learning how to make good use of it for societal decision-making and resource protection. But it is all of these things, and I think this slide, I wanted to show this slide also because it reminds me, and should remind all of us, how many players, how many partners it takes to do this, what sort of constructive and productive partnerships and communications and trust it takes to sustain this capability that we now have here on planet Earth. So, this is the little blue marble we live on. This is from NOAA's Sumi MPP satellite. We really should have named it Aqua, not Terra. It is really mostly water, so, but there you go. And I want to give thanks to all the folks listed there on the upper right. They are really the brains and the work and the effort that is making possible all of the things that I've told you about. I have the great privilege of being the face and the mouth that gets to say these things, but it is quite a spectacular team. The prospect that we have here with the MBON initiative is very exciting, and we really wanted to showcase and announce it here at IUCN with the strong focus on protecting and preserving our oceans this week, because it's just a great tool that we will all be relying on in the future, I'm sure. So with that, I want to thank you very much for your attention, and depending on Nicole's wristwatch, I will happily take some questions.
If you have a question, please raise your hand. Excellent. Eric, could you go over there?
Thank you for being here and communicating all of this to us. Have you gone to the Hill and tried to communicate this message back to Congress? And is it changing the reception that you're getting to science and the importance of science for us to make the critical decisions?
You can imagine in my role, I spend quite a lot of time talking to the United States Congress and to government partners through different forums as well. So I serve on the group on Earth observations with people of my similar rank from the European Commission, from China, from South Africa. We are the co-chairs. GEO is now 105 nations that are working collaboratively on this effort for global data sharing and Earth observations. I do find, I would say I do find in the United States Congress, when you illustrate that set of links, that value chain, if you will, from the science to the societal need, the societal question, whether that's public health or good resource management, that's a connection they get. I think the science itself can seem a bit esoteric. It may lead some people to wonder, how much do I actually need? I would say we are in the United States, the philosophy towards funding science certainly has changed in the decades since the early Cold War years. I think there was much more of a patience back in, say, the 60s, 50s and 60s. You let good, smart scientists go do, they will guide the work as best as anybody can, and the results will percolate out to the benefit of society. There's now more a desire for some active, intentional driving of that benefit to society, not just put it in the journal and sit back and wait. And so we're seeing more and more people from both the policy side and the science side, I think, working to bridge those gaps, to understand societal needs and to more actively make the connections of science, data, and information to societal benefit. That's really NOAA's forte. We kind of sit right at that middle spot. We've tremendous scientific talent within our agency, but we also harvest from other national and global partners good science anywhere we get it. And we're very much attuned towards what are the societal issues and needs that Earth science could contribute to, and how do we help foster and catalyze that connection. It's the reason I love being at NOAA, because it goes all the way back to that inspiration I had looking out the window of a spaceship, that it wasn't enough for me to just be able to come home with really cool vacation pictures and show people neat scenes. I wanted to find ways to make this actually matter in very meaningful ways, and that's the essence of NOAA's business.
I think we have time for one more question.
All this data collection, everything is absolutely fabulous, but I feel that still the average person doesn't give a damn, unfortunately. Many, many of them. And they don't do their own little tiny bit to help. And I think maybe more education, right, from the beginning in schools, or even for adults, any way that information can get out to the wider world would be. Have you any views on that?
I couldn't agree more. I from a very young age was fascinated by the planet, so I'm always a bit amazed that people are not as fascinated as I am about the planet. I think getting the data and information out, getting education out is one thing, and we certainly could do more and do better jobs of that. The other thing that I find, though, is that really, more often than not, is storytelling that makes the connection, or a connection that prompts someone to feel or think differently about it. People don't change their mind because they heard something or learned. They change because they experienced something. And it very often is the human connection of hearing a a poignant or a moving or an inspiring story from another person that sets, flips the switch and makes them realize there's a connection of that to me. It's sometimes just a small bit of an increment. It's not always the scales fall from their eyes and they are magically completely different. But I think the power of storytelling and the importance of human storytelling is very, very high in that regard. Thank you all again.
Thank you, Dr. Sullivan. It was an honor to have you here and a very informative presentation. If you'd like to go back and watch it, we'll have it available on YouTube, and you can check out, I know that the screens around here have the YouTube URL, or come and find me after. So thank you again, and we hope to see you at later events. Take care.